All right, we'll go ahead and we'll get started. So I'd like to welcome all of you out to our webinar today. My name is Nathan Eliason. I'm a senior technical specialist at KETIV. I've been working with KETIV now for about 5 years. And before that, I worked at Autodesk for about 7 years. So I've been in the CAD industry a long time, and one of my personal passions has been automation. I like to think through processes and think how can we make design faster, how can we respond to our customers faster, and how can we give them better service, making sure they have the products that they need. Now, I'm also joined today by Stacy Menson. She's our Director of Marketing. Would you like to just take a minute to introduce yourself, Stacy?
Hey there, everyone. I am Stacy Menson, Director of Marketing at KETIV. I've been with KETIV for about a year, and prior to that, I was in the engineering consulting field. I help with all things events, marketing, webinars, and all of that fun stuff. So I'll be here really monitoring the chat for questions. You can tag them in the Q&A, as well as sending some links out as Nathan's going through some things. So I'll let Nathan get started.
All right, thank you very much. So why we're here today, as I mentioned, we really look at you guys as our partners. We want to partner with you guys. We want to help you be more competitive. We want to help you be more successful out in the business world. And so what we want to do is we want to start sharing knowledge with you guys. How do you start learning how to prepare for automation? If you guys can do engineering much, much faster in the future when the economy comes back, it's going to put you in a position of strength. And so as your partner, we want to help you guys get started. We want to give you tools, resources, whatever you guys need so that you can start and look at improving your overall process. Now, for our meeting today, I want to cover 4 main parts. I want to first just give an overview of what automation is, what its purpose is. Then I want to talk about some best practices. We've been part of a lot of these different engagements with companies, and we've seen some companies that have started to create their own automation and kind of program themselves into a corner that's kind of hard to get out of. And so we want to start sharing with you guys some best practices so that as you come up with your own automation solutions, you can avoid some traps that might cause problems down the road. We also want to talk to you guys about automation projects in general. What does it take to do an automation project? What are the steps that you have to do in order to have a successful automation come out as a final deliverable? And then at the end, I will open it up for some Q&A. But like I said, we're going to just kind of keep it closed until the end. And so if you have a question, send it into the chat window. And at the end, Stacy will make sure that we address and answer each of the questions that came up. And we can potentially also open it up so that you guys can speak and ask your questions as well. So to give a quick overview of automation, when I think of the word automation, a lot of times, just me personally, I think of some type of a robotic arm or an automated assembly line or an automated welding robot that instead of having a person do the same action over and over and over again, we have machines that can do it more efficiently. We have machines that don't get tired, don't get sick. They can be very predictable, and they basically help us improve the overall output that we can create from a manufacturing standpoint. Now, when we look at that same principle or concept from a CAD perspective, we basically want to do the same thing inside of our CAD tool, right? Here we have our CAD tool, and instead of creating an actual product, a physical product, like with a robotic arm or an assembly line or something, we actually want to automate the design of that product. So we want to make it fast. We want to make it so that the user very simply can go in and type in some parameters, some input information, and based on that, the design creates itself, and at the other end, we can create drawings, we can create bills of materials, we can create pictures, images, whatever we need in order to provide our customers or our manufacturing department or anyone else the information that they need. Now, with a typical automation solution, there are several parts that are key. Most of what we build is centered around Autodesk Inventor. It's a robust CAD solutions that's been around for decades now. And then what we do is we usually do some programming on top of that, and that creates what we call an Inventor add-in. So if you think of when you're inside of Inventor, how you have buttons for extrude, you have buttons for revolve or other types of features, we can create buttons inside of Inventor that run our special utilities that design your product faster. And that's what an Inventor add-in is. Now, in order for the add-in to work, we typically need a bunch of start parts, like you need your bolts, you need your screws, you need brackets, you need other types of common components that go into your solution. And then generally, sometimes there's like an options database. It can be as simple as an Excel spreadsheet. We can make it fancier than that if it needs to be. But the point is that you have to combine informational data like rules with actual CAD models, and together you put those together to automate the creation of your designs. Now, there are different types of automations that we can create. And there's two main ones that I want to talk about right now, even though there are definitely other types that can be created. One of them is what I call a dialogue-driven solution. And that's where you have some kind of user interface that lets you put in a job number, lets you put in information. Like in this case, we're just giving an example of a bare tank configuration. So you might say, what's your tank diameter? What's the tank height? So you might ask for different types of information. Then when you hit the build tank or the go button, then Inventor takes that information and automatically configures a model based on the information that you said you needed. Then from that 3D model, as I mentioned, we can create 2D drawings. We can create all kinds of other information as well. Now we also have what I call kind of like a design accelerator automation. For those of you familiar with Inventor, we have what are called design accelerators. And what those are is those are special built tools. Like if you want to build a shaft real quickly, or a spur gear system, or a V-belt system, instead of creating all the individual components, you can click these tools, put in information about what you need, and then it will automatically bring in a component and place it where you need it. And so this one isn't automatic in the sense that you type in a bunch of values and out the other end pops out a magical assembly exactly the way you want it. This one requires more interaction, where you pick surfaces, you pick lines, you pick different parts of your assembly, and then based on the options that you pick, then it places the component where you need it. So that's what I call design accelerator. It's something that isn't automatic from a dialogue perspective, and it requires interaction with your model. Now, this right here is an example of one of the design accelerators in action. So this is the belt-driven automation. And as you can see here, I have an assembly of a motor and some type of shaft that I want to be able to spin based on that motor. Now, if I didn't have these tools inside of Inventor to automatically go in and create a belt assembly, which you're going to see start right here, then I would have to go in and I'd have to create every single one of these pulleys. I'd have to go in and place them exactly where I want them. Then I'd have to go in and I'd actually have to create the belt that connects all of those together. So you can see that would be quite a bit of work to do all of that manually. Here with this tool, I could just simply select the shaft I want it to line up with. I can select where I want it to go. And based on all of these different options, it will automatically key my shaft for me. It will build all of my pulleys. It will automatically generate these belt models. It'll do all of that for me. And even better, if I go in and make changes down the road, then it will automatically update as well. So that's what we mean by that type of an automation. It's something that requires you to click in the model, and it's very interactive versus being something that you just type in values and out the other end comes your final result. Now we also have another type of automation that I call building block automation. And what this is about is if you have like assemblies that always consist of the same components that kind of snap together, then what we can do here is that we can build a library of your common components. And these components can just drag and drop right into an assembly. and we can build these connectors that snap together. The advantage of something like this is that it's much, much easier to create, and it really doesn't require a whole lot of programming because we're utilizing a lot of functionality that exists within the factory design utilities and the product design and manufacturing collection. So in this case, we were working with a customer that they build these sizers, and they wanted these sizers to be easier to bid. So they weren't looking for full engineering models. They were really looking for streamlining, getting a bid out to their customers quickly as possible. And they wanted to be able to create 3D models really, really fast. So later on, I actually have a video that will walk through how that one works. But for now, I just want to point out that it basically just involves setting up this library, setting up how you want the components to snap together, and from there, you can quickly create any type of configuration you want by dragging and dropping these components. So the different kind of CAD automations that I want to talk about, these are different tasks, different types of automation that we've created in the past. We have automations where we automate different tasks. We have an example that I was just talking about, sales to CAD automation, where they're more concerned about the bid stage versus the engineering stage. Then we have engineering design automation, which is where you want everything designed down to the most minute detail so that you can create engineering drawings or other types of output to actually create the assemblies. And then finally, we have manufacturing automation, which again would be like drawing packages, supplier collaborations, and so forth. Now, from a task automation standpoint, a lot of this really goes or revolves around managing your data. So a lot of times when drawings are created, a lot of companies standardize on PDFs. They're like, hey, after we create the drawing, we want a PDF because we can send that to suppliers, we can send that to the shop floor. You know, pretty much everyone can read a PDF file. Or maybe they need a step file so that they can send it out to a specific machine and have some data created from it. Or maybe they need a DXF so that they can send it out to a laser machine and have the profile automatically cut out. So whenever we have to take an existing model and create a specific type of output for different types of machines or different people or different purposes, that's something that we can help automate, is generation of those types of files. We find that a lot of engineers can spend hours, creating PDF steps, DXFs, and really it's easy to automate. So it's something that you should try to eliminate if you can. We can also route output files to shared locations. So not only can we create those files, but if you need it to go to a network folder, a cloud-based folder, somewhere where the shop floor can easily access it so that they're not getting their hands where your engineering data is, we can go and we can route those wherever you need them to go. And then another common ask that we get around task automation is sending out emails. So, when you release a product or when a part has been changed and gets set back to the release state, oftentimes you want to notify different people what's happened. And you can manually generate that email, but of course, as we know, anytime something's manual, there's a potential that it could get missed. And so there are ways that we can, automatically generate emails based on when different products go into a release state. Now, obviously, that's assuming that you have a tool like Vault that manages those files, but the key here is that you need to think about common things that you're doing over and over again, like these little tedious tasks that if you were to add up your time, you might find that you're spending hours a week doing these little tedious tasks, and those are great candidates to start automating first. As I mentioned before, we had this project where we wanted to take these sizers. They wanted to be able to capture 70–80% of the design intent at the time that they actually were making the sale. This would make it easier for them to upsell options. It would make it easier to quote, and more importantly to them also, it would they would be able to give models to their customers so that they could then put this inside of their own models. So there were a lot of benefits for them to be able to create a 3D model up front versus the old way of creating drawings inside of AutoCAD. So I'm going to go ahead and let this video play.
When responding to RFQs from customers, Imagine the ability to quickly configure a machine
Can you guys hear it
to
okay?
their exact specifications and being able to do so with simple, easy-to-use tools.
Okay, good.
In this concept, we have a library of common parts that are used to create unique configurations of sizers. A solutions engineer, without the need to understand complex CAD tools, can drag the various components they need from the library and then place them where needed inside their assembly. It's basically like having a box of Legos where all the pieces understand how they go together in an intelligent manner. Once the pieces are brought in, connectors act like magnets, so all the parts snap together perfectly. Another advantage of this tool is that a 3D representation of the overall project is being created. 3D models are useful for many reasons. Examples include providing the customer with a 3D model so they can check form and fit of the system, extracting a bill of materials to generate pricing for quotes, creating 2D installation drawings and maintenance instructions, or rendering images for a quote so that the customer gets an exact idea of what they will be purchasing. Now, so far we've seen that parts can snap together, but these connectors also have the ability to share information with other components so they can be sized properly. As an example, notice here that the default size of the trolley is smaller than the sizer we're configuring. As it connects to the machine, intelligence within the model tells the part to update automatically to the correct length. Additionally, as sizes of components are modified, any affected systems get updated automatically. Notice that as the length of the midsections change, they all move down to show the system is now longer, and the carrier motor assembly moves with them. Now, each component in the library can hold parameters that allow changes to be configured inside the model. To move a sensor bar, or even the location of the trolley, simply inputting the desired location will update their positions. In this case, notice we have some interference between the midsection leg and the crossbelt. These problems are easy to catch with 3D models and can avoid costly field issues when these don't get fixed before going out to the customer. Here we can change the location and the problem's fixed. We can also embed important rules in models to avoid typical design mistakes. One such rule is that 2 motors must be used for the carrier if the sizer has 8 or more lanes. If we try to change a 10-lane sizer to just 1 motor, notice that nothing happens. However, if I change the system to 6 lanes and then ask for 1 motor, this system lets me move forward. Oh, and by the way, if one component in the system is changed to just 6 lanes, guess what? They all change. This intelligence is passed from connector to connector, and this magic keeps all the components at the right size for the job. Now, as one final example, we'll change one crossbelt to the deep configuration and then change the width. Notice that the standard extension width updates automatically, even though I didn't tell it specifically to do so. And as one last rule, if the standard extension goes past 1,000 millimeters, we'll go ahead and add supports, even though they aren't present in shorter versions of the standard extension. All these great tools allow solutions engineers to focus on what the customer wants instead of focusing on the CAD tools.
All right, so hopefully that was explanatory to give you an idea of different types of ways that you can automate what you guys need to produce in engineering for your, whether it's for your customers, for manufacturing, for sales, you know, whoever you're working with, there are different options on how we can create automation, how we can help make redundant tasks go a whole lot faster. Now, what I want to do right now is I want to talk about, I'm actually going to the next slide here. I'm sorry. I wanted to talk a little bit about generative design, and we're going to get into a discussion about generative design versus what we call a master model design. And these are 2 different ways. And most people, when they're first starting to learn how to automate and they're first starting their automation journey, they'll learn tools like iLogic. And when they learn iLogic, they'll do master model approaches, which I'll explain in a minute. What a master model approach is you actually start with an assembly that has pretty much every variation built into it. Then based on different options that your user selects, you have rules that go in and that will hide, will suppress, will do whatever it takes so that it pairs the solution down to exactly what they configured. The difference between that and a generative design is a generative design will basically start with, think of it as like being an empty assembly. And with that empty assembly, you go ahead, you type in the parameters, and then it builds from the ground up what you need. That's generally the approach that we take in most cases. There are some cases where a master model approach works really well, but there's also some gotchas with master modeling approaches that you have to be really, really cautious of. So to give you an example, you can see right here inside of Inventor, let's see if this is playing, we don't have any assembly. There's no geometry, right? All we have is this little form that lets us configure a tank. So when we go in and we add all of the different parameters that we want to create and click done, notice that what this is going to do is it's going to basically build it from the ground up. So whereas before our model tree would have been completely empty, this actually builds everything up from the ground all the way up. So you can see we quickly created 155 components without having anything in the model beforehand. Now, what's nice about that is that when you build this generatively, when it's done building it, it's just the same as if you had built this typically inside of Inventor, which means it's easier to go in and edit. You can hide parts, you can move parts around, you can poke holes in new parts. There's a lot of flexibility that it adds when we build it from the ground up. Whereas when you use the master model approach, typically those rules are built right into your actual 3D model, which means that anytime you try to move something, you might have rules that move it back, you might have rules that change it. So because of that, it's, we typically, like I said, in 90% of the cases, we will build generative design-based solutions. Now, the last type of automation that I wanted to go into is the manufacturing automation. As I mentioned, this is where we can take the 3D models, because again, remember, everything typically is focused around those 3D models that we generate. But because those 3D models, Inventor specifically automatically knows what the bill of material is, we can extract that bill of materials. We can create cut sheets and we can send it to suppliers. If you have a bunch of cut components, we can filter those out and take those out so that we can get all the cut links and put that onto drawings. There are also ways that we can do online design review and red lines. And that's not even automation. Those are just tools really that help you communicate better with your manufacturers. Inventor has some of those that are built out of the box if you look up shared views. That's one way that we can do that. We even had, some companies came to us and said they needed to etch part numbers on sheet metal parts. And so, we worked with them to figure out how we could take in their flat assemblies and put the part number where it needed to be and automate the creation of all of those types of features. So a lot of different ways that we can do automation. The key here is that whenever you're building or designing an automation solution, you really need to start with the end in mind. You need to think, what are the ultimate deliverables that I need to create or that I may need to create down the road? And then you need to work backwards from there to make sure that everything you automate is going to work right. Now, I do want to take a minute to talk about something that's very important with automation. Before you automate anything, my suggestion is to first have a manual process that works really robustly and that is repeatable time and time again. If you automate a bad process, it's still going to be a bad process. Automation will not magically fix a broken workflow to be successful. What automation will do is it will take a good process that you have down and it will automate it and make it way faster so that you can produce your outputs at a lightning fast speed versus having to do the same steps over and over again in a manual fashion. So I do want to point out that really step one to any automation is first make sure that what you're going to automate has a robust manual process that works well, that is robust, and that will meet the needs of the different types of inputs you want to allow your user to make. So now let's talk about best practices. So I mentioned this before, and we have a couple of different options that I discussed, generative design versus master model. Now, as I mentioned before, master model, we start with this template. You can see here in this assembly, everything's here. And when you go in and you make changes to the dialog box, it basically takes these components and it changes them. It changes patterns, it suppresses parts, it unsuppresses parts. It can even go to other parts and it can change them so that it changes the size, the shape, the geometry. But the point is that you have to start with something already there. That's the way master model works. Then generative design, on the other hand, you start with a blank assembly. So you can see here we have no geometry, just a form. And when you go in and you fill out the different options you want in that form and you click apply or go, then it automatically goes in and one by one, it will bring in every single part, place it where it needs it, and then go to the next part. And it'll keep repeating that process till it's done creating the whole entire design. Now, to compare the two from a qualitative standpoint, again, in generative design, we start with a blank slate. In a master model, we start with a pre-existing model. Generative design, parts are created as they're needed. So based on the options we pick, if we need part 1 or subassembly 1, we can go grab that, bring it in, and put it inside of our assembly. Whereas master model, existing parts are modified. So the parts already have to exist. In generative design, they're placed in assembly as needed. I just mentioned that. And then overall, we consider generative design really to be a more robust solution, whereas master models are more complicated to save out. Now, I want to bring up a couple of things that gotchas that you need to be careful of if you do decide to move forward with the master model approach. Because like I said, this really is easier. I mean, it's easy to learn how to do master model approach. And because of that, most people will start here. And I'm not saying don't start here, because this really is a good starting point to help you understand how you change parameters in parts, how you pass information from an assembly down to parts. It's a really good place to start. But you do need to be aware of some of the limitations here. One of the limitations is that when you do master model and you want to suppress or unsuppress parts, Inventor is going to require you to use a level of detail. And you cannot have the master level of detail selected if you're going to be suppressing and unsuppressing parts. So a lot of times what programmers will do is they'll create a separate level of detail that's called iLogic, or whatever you want to call it, and make sure that that's always the active LOD. If that's the active LOD, then you can suppress and unsuppress all that you want. So that's one of the things. Another thing that you want to be careful of is I've seen it where someone's created a master model, and the problem is if I configure a master model, I kind of save that as its own unit. Then when I want to create a new version of it, I copy all of those files over and I open it, I put in my options, and now I save that out as a new one. And then I keep doing that over and over again. And the problem with that workflow is that a lot of times there are common components that don't ever change, right? They're always the same from one assembly to the next. And sometimes when you do the master model, you're copying parts over and over and over again. So you're making 1,000 copies of a screw or a bolt or of a specific bracket that never changes and is always the same for every single assembly. Now, if that doesn't mess up your workflow, like literally every customer orders their own unique thing and you don't care, I mean, that's fine. But when you get into a data management perspective, we highly recommend reusing components that are common rather than recreating them over and over again. It's much better that way. Then if that part ever changes down the road, you don't have to change 1,000 different parts that are all over the place. You can just change it once and it will update inside of all of your different assemblies where you used it. So because of that, with generative design, typically we'll have that library, and if a part doesn't change, we're just going to pull it over as is and reuse it over and over again, instead of constantly creating new copies of it. And so that's one of those areas where generative design really helps to make the process more robust and more smooth. Now, I also want to talk about iLogic versus Visual Studio. Apologize here. Gotta move around here. So with iLogic, you know, obviously that's an environment that comes built right into Inventor. And like I mentioned, it's a simple interface to start with. It's a great place to learn. It's actually where I recommend everybody start if you don't have any existing programming experience or automation experience with CAD tools. iLogic uses the Visual Basic language, which is a very popular language. It's easy to learn. It's probably one of the most easy ones to learn because it's one of the ones that sounds closer to English. You know, as you learn a lot of the commands, you'll see that it's not really that hard. It's approachable. The other nice thing about iLogic is it's embedded inside of the CAD models, which makes it really easy to reference different components, different parameters. It makes it easy to control all of that. It's easy to create user interfaces. We have a drag and drop tool right inside of iLogic. So if you want to create a form where someone can go and type in their inputs or options without even knowing how to program, you can create a simple user interface. One of the downsides is that there's limited debugging tools. You know, I think Autodesk is looking at enhancing the debugging tools that are available inside of iLogic. But for today, it is limited what you can do. And it's also, you can't really create custom add-ins. And I mean, there are ways that you can create your own buttons inside of the interface and that you can change the interface to look the way that you want, like add more buttons and things like that. But it's not really recommended. It's not as robust as if you were to actually create an add-in. And again, an add-in is something like the design accelerators that has their own custom ribbon, their own buttons, their own icons. You know, you can do all of that when you create an add-in. Now, Visual Studio, on the other hand, it's also a very robust tool. It also uses Visual Basic. There are some differences between the version of, actually I take that back. I think the API is the same between iLogic and Visual Studio for Inventor, but Visual Basic does, I think, have a little bit of differences between the two. But anyway, Visual Studio uses Visual Basic also. It also gives you the option to program in C# if you prefer that language over Visual Basic. Inventor does have an API for both of those. So with the Inventor API, you can program in C# or Visual Basic. It is a more complex design environment, which is good and bad. The bad of it is that it does take more effort to learn. You know, it is more complicated, so you have to definitely put forth a much bigger effort to learn how to use it. But along with that, it's also more powerful what you can do. There's a whole lot of ways that you can, you know, automate. You can detect when a surface has been selected and then decide what you want to do with that surface. So, I mean, there's a lot of really cool things that we can do inside of Visual Studio. The other thing is that the programming is always done outside of the models. It's not embedded. That's your only option with Visual Studio. You can build really complex user interfaces. You know, like in iLogic, we can use simple ones that have little drop downs and text boxes and things like that. But when you go to Visual Studio, I mean, pretty much sky's the limit on any type of an interface that you want to build. They also have a robust set of debugging tools. So when something goes wrong, it's easy to capture what's going wrong. And, you know, you can put stop points in your code. You can do all kinds of things to make sure you can watch variables and track them as it goes through the code to see if things aren't updating the way that you expect them to. And as I mentioned, you can create custom add-ins. And with custom add-ins, you can set that up inside of Inventor where, you know, anytime you fire Inventor, it's automatically loaded and your custom tools are right there for the user to start using right away. So the last part I want to go in for the presentation today, I wanted to talk, you know, about what it takes in order to go through a successful automation project. So really, when you look at automation projects, there's 4 main phases that you want to break it down into. The first part is scoping the project. And this is where we define the overall needs and requirements of the project itself. Then we need to make sure that we have all of the models that we need. That might be part models, it might be assembly models, but we need to make sure we have models that are robust and that update the way we expect them to when we make changes. Then we actually build the project, and that's where we start building the rules engine behind the scene that makes sure that everything updates appropriately. And then we have the testing phase. And obviously the testing phase, this is actually very, very important. And up front, even in the project scoping phase, you should come up with a range of different inputs that you want this to support. And typically, if this is an existing product line, you should have examples of different types of variations that have been created over the years. And it's good to pick different variations that you know what the output should be. Then when you run those through the system, you can verify and validate whether the rules are correct or whether they still need some work to get to be more robust. So from project scoping, one of the things we do is we define the CAD modeling needs, so what models need to be created, what parameters in those models need to be configurable so that we can pass parameters and have our models update correctly as we put them together. Then we document rules for the final model. So, if we change this input, does it make my assembly longer? Does it make it taller? Does it mean that I need one subassembly versus a different subassembly? So we document all those types of rules so that we can then build the final solution. We also, as I mentioned earlier, you want to really start with the end in mind when you're doing an automation project. And so defining the required solution outputs is extremely important. Again, if you're not going for CAD level, or I'm sorry, manufacturing level drawings, then your models don't have to have a lot of detail in it. And you can simplify the models and make the solution run much faster and more efficiently. On the other hand, if you need every little detail defined, then we know that we have to make models that are much more detailed and that have, every hole, every fillet, every type of detail in it that we need. And then the final thing is we review the user interface needs and requirements. So again, how are you going to interact? You want drag and drop capabilities? Do you just need a form that comes up and people type in what they want and your model and other deliverables get created automatically from that? Do you need some interactivity with Inventor? So these are important to understand so that we can, again, steer you in the right direction of where you should go when you're developing your automation solution. So with all of the planning done, then we go ahead and we create the 3D CAD part models. And by part models, understand I also mean assembly, right? Just any Inventor models that we need. Some of them will be static. Like if there are some sub-assemblies that never change, then we'll just create that whole entire assembly and we'll bring that in and use it as a static assembly whenever it's needed. If it's an assembly that can change, then we'll make sure that we have that sub-assembly with the right logic it needs so that it can update first before it comes into the top level assembly. Then we'll test CAD models for proper updating. I do want to point out one thing that's interesting. When we look at really, really large assemblies, we've worked with a few customers that have these large assemblies. And they tell us, the performance, it's a little slow to develop everything because we have so many parts. And there's 2 different ways that we assemble parts inside of the assemblies. One way is probably the traditional way that most people do it manually, where if I insert a component into an assembly, I'm going to use constraints or the assemble command, right, or joints. So I'm going to say these 2 faces made up together, these 2 edges align, these 2 axes align. I'm going to probably use tools like that to set constraints and put my parts together. It's fantastic to do that when you're doing it manually, but when you're making these big, huge models, Inventor has to go through and has to update every single constraint that you create like that. And when you have a huge assembly, I mean, you could be talking about tens of thousands, maybe even hundreds of thousands of different constraints that it has to ensure everything is there, everything is properly, you know, mated together. And my point in saying that is it can take a long time because it's just a lot of information that Inventor has to go through. So a lot of times what we'll do with larger assemblies to increase the performance is we'll bring it in, we'll orient the model, we'll put it exactly where it needs to be in space, and then we'll just lock it down. And the advantage of doing it that way is now you don't have a million different, probably not a million, but you don't have thousands or tens of thousands of different relationships or constraints that have to be resolved before you can open up your model and actually start getting information from it. So I just want to make you guys aware of that. Even when we create these assemblies, there's a couple different ways that we can potentially do it. And then, of course, getting back to our model creation slide here, if drawings are one of your outputs, then we also need to create those templates so that when we feed parts to it, the drawing templates know how to handle those models and update themselves automatically. Now, I do want to also point out that drawings are probably the hardest part to automate and take the most time. And I think it's important that you guys understand that. You know, there are a couple different ways. If you have a drawing template, if you have a part that always has the exact same features and there's a dimension somewhere, those typically we can automate better and easier because you can actually create a template that has all the dimensions laid out, and then all we have to do is send a new part to it and it'll automatically update and change the dimensions according to the model, and that's great. But there are situations where who knows what you're going to get by the time the automation is done, and so you have to create you have to automate the drawing through code, and that gets a lot trickier. And that's because you don't know what dimensions are going to be applicable, which ones aren't going to be applicable, and that takes a lot more coding, and you have to do that with the Inventor API. Because of that, we did have, you know, we know a lot of companies are interested in learning how to automate drawings better, which is why we had the AVA on that topic 3 weeks ago. So if that is something of interest to you, I encourage you guys to look at that, you know, to watch that AVA session so that you understand at a much deeper level what it takes to automate drawings. But it is one of those things that you have to be really careful about. You have to sometimes build features into your 3D models that you can then reference when you're creating the drawings. Sometimes those might be points, they might be planes, they might be, you know, lines, different things like that. But my point is you have to really think through when you want to automate 2D drawings in a way that you're building everything through code. The third step is actually building the project. And like I mentioned, the real main part of this is building that rules engine that controls model changes. You know, that's key. That's basically all of your logic that tells parts how to change size, how they go together. So really the bulk of the work on any automation is really building that rules engine. Then we create the 3D model outputs. And what I mean by that is we now are able to take those base 3D models we started with, run them through our rules engine, have them change appropriately, and come out the other end configured the way that they need to be. Then we create 2D drawing and other, you know, if you have bill of material or other type of document outputs, we'll do that. And then usually at the end, we'll create the user interface. Now, sometimes if a solution is really reliant on the information that comes from the user interface, we might create that first and then the automation next. Really, the order doesn't matter, but most of the time, that's something that we'll create at the end just to make it easy to interact with it, make it so that people don't have to know Inventor really well in order to be able to configure their product. From there, we do solution testing. You know, just because it works on our computers or your computer doesn't mean it will work on other people's computers. So it's important to deliver the solution and install it in someone else's environment to test what issues are we going to go through there. once we get that running in a customer environment, then you can run testing against the use cases that we defined in the scoping phase. You guys would identify, your users identify any issues with the outputs. And then the solution, we kind of go through an iterative process of fixing it until all of those little bugs and gotchas get worked out. And then, at that point you can say, okay, our solution is done. It's ready for release, and you can start using it on other projects. Now, I do recommend that when you start using a new automation tool, you definitely need to manually check the outputs to make sure that it's working properly. And over time, as you see it working properly over and over again, then you can start reducing the amount of due diligence you do, that you have to do after it creates each unique instance. So that concludes the information I wanted to cover today. Like I said, I wanted to kind of give you guys, I was hoping to spur some thinking about what are the different ways we can create automation. Start thinking about product lines that you guys have where it might make sense to automate it to make it go faster. All right, well, thank you everyone, and good luck with your automating needs, and we hope to be talking with each of you in the next week or so on how you guys can get started on your journey to automation. Thanks so much and have a great day.